All right, the method of transformations. Method of transformations. Is related to the previous videos. It's sort of an offshoot of that. But it turns out that if you can relate one random variable to another via a strictly increasing or strictly decreasing function, then you have a simple way to get the density of one from the density of the other without having to get the CDF along the way. So suppose, first of all, that h of y is increasing in y. Okay, that is that it looks something like this. Okay, here's the y-axis going along this way. Maybe it's some function, I don't know, it looks like this, something like that. Note that, you know, if this is our function h. Now h has an inverse function, all right, and it's, if you remember, or even if you don't, from your pre-cal or some other math class, that these inverse, well, that's not very good, is it? But it's supposed to be, it's the function that you get when it's reflected in the y, in the line y equals x, right? Okay, so this would be h inverse. Okay, so suppose you have one random variable u defined to be a function of this other one, you know, where the function that does the mapping is this h function. Okay, then and you know, again, as an example, see how this might be of use. You might think of y as some random demand for a product, and u is some profit. Okay, it's a that may be a linear or some kind of increasing function of profit. Okay, maybe not necessarily linear. Okay, then the CDF of u is that guy is defined to be, of course, the probability that u is less or equal to little u, which is the probability that h of y is less or equal to little u, right? Just subbing in there, right? The h of y for u. But this is the same thing, since h has an inverse, this is the same thing as y being less or equal to h inverse of u, right? So, you know, long story short, or short story shorter, we can express the CDF of u as the CDF of y evaluated here at h inverse of little u, right? Now, let's see. So we're sort of doing this in general, right? We're not doing it for one specific problem. Let's see if I can now use this expression to write down an expression for the probability density function for u. So that guy is going to look like this, right? F sub u of u, that's the probability density function for u. It's, of course, it's the derivative with respect to u of the CDF of u. Okay, so this is the derivative with respect to u of the CDF of y evaluated at h inverse of u using that previous stuff that we just did, right? I know that this is equal to that. Now, if I carry this out, how do you take the derivative of all this stuff? It's a function of u. Okay, a derivative of all that with respect to u. Well, I could think of it like this, right? It's d dx of f sub y of x evaluated here at h inverse of u times the derivative of the argument, right? D du of h inverse of u, right? And so I can write that then as this is, what is this? If I differentiate this CDF with respect to its argument and then evaluate it there, the derivative of the CDF is just the PDF, right? So this is the PDF of y, h evaluated at h inverse of u, times d du of h inverse of u. Very good. Okay. So that is very useful. That meaning this. Okay. It allows us, if you can relate the random variables u and y via an increasing function in y, then you can quickly get the PDF for u by carrying this out. Now let's suppose that h is actually a decreasing function in y. H is decreasing in y. That is that maybe we can express our random variable u as h of y, and that's something that's decreasing in y. Well, now, so let's take a look at the CDF for u. This is the CDF for u, right? That's exactly what that is. That's f sub u of u. Then this, note that, okay, if I make a mark here, here's my u-axis, right? So the random variable u is less or equal to this mark if and only if, what? If and only if my random variable y is at least this mark, which is h inverse of u, right? So this is equal to the chance that y is at least h inverse of u. Another way to say this is that f sub u of u is equal to 1 minus the CDF of y evaluated at h inverse of u. Okay? So now let's differentiate this guy, because I know that what we ultimately want to get out of all of this is lots of money and fame. But aside from that is we want to get the PDF probability density function for u. This I know is going to be the derivative with respect to u of the CDF of u. Whoops, CDF of u. Okay, and so that's going to be the derivative of all this stuff, right? Which is going to be negative d du of f sub y of h inverse of u. Now that looks a lot like what we had just a moment ago when h was an increasing function. Okay, and so in fact all this is going to work out to be negative probability density function for y evaluated at h inverse of u times the derivative of h inverse of u with respect to u. Okay. Now, so it looks a little different, right? Before we didn't have the minus sign. Okay. Now we have a minus sign here, but hey, guess what? Take a look. Okay, so h is a decreasing function of u. What does h inverse look like? Remember, these increasing and decreasing functions have inverses, right? And again, they're just the functions that they're just reflected in that line right there, right? So this guy, this is what h inverse looks like, and it's also a decreasing function. It's also a decreasing function. Okay, so this guy is this derivative is actually going to be negative. So I can in fact say that this is just it's going to be the density function for y evaluated at h inverse of u times, we just say it like this, the absolute value of the derivative with respect to u of h inverse of u. And in fact then, now what we can say is, so this in fact, it looks just the same as what we had before, right? It looks just the same as what we had before. Because before, we had something like that. So what we can say is a more general, all-encompassing statement here. Suppose h is increasing or decreasing. Not both, but either one. Then f sub u of u, the density function for u can just be expressed as the density for y evaluated at h inverse of u times the absolute value of the derivative with respect to u of h inverse of u. Oops, absolute value, okay? And this is for u when u is expressed as this function of y, okay? And so this is related to the method of distribution functions, but remember the method of distribution functions, the idea is you want to go from one probability density function to another, right? If I know how y behaves and I have the PDF of it, then I want to know ultimately what the PDF of u is, okay? What this gets us though is that if h is a strictly increasing function or decreasing function, then this gives us a way to get the probability density function for u without getting without having to go through the cumulative distribution function stuff, right? If I know my function h, I can get the inverse real quick. That's probably not a problem. I can take a derivative of that, get the absolute value, and use the density function evaluated at h inverse of u. Okay, so we don't have that intermediate stuff there, getting having to deal with the CDF.